In this video, we'll cover the problem, escape the space station. We'll talk about what the question is asking, we'll talk about some of the key gotchas with this question, and then we'll see how to solve it in code. To start, I want to break down everything that's on the screen because there's a lot of information. The very first thing is go ahead and ignore the grid that you can see on the right-hand side of the screen. For now, we're not going to talk about that, but it'll become relevant later. Now, as for the left-hand side, the idea of this question is that you're trapped on a space station and you need to find out how to escape. The input you'll be given is going to be a map, and that's represented as a grid that contains zeros and ones like you can see here. A zero means that that particular location is something that you can pass through. It's totally fine. A one means that that location is a wall. You're not allowed to pass through it. So you're going to start in the bottom right corner of the input grid, like I've marked here. And your end goal, is to end up at the top left corner of the grid right here. You need to figure out the shortest path, or the length of the shortest path, from your starting position to your end position. But there is one key note, which is that you're allowed to remove at most one wall. So you can remove 0 or 1, whatever allows you to reach the optimal path. So we start in the bottom right. We need to get to the top left. We're allowed to remove one wall, but other than that, we cannot pass through any of these walls, and we need to figure out the length of the shortest path. So as far as the example here, the answer is 21. You can see I've numbered all of the different nodes that we would travel through, starting from the start node in the bottom right corner of the screen, going all the way to the left, and then up and to the right, and up and to the left until we hit the finish node right here. So there are a total of 21 nodes that we touch throughout that path. You'll notice that we actually do count the start node and the end node in that calculation. That's important. Okay, so now let's start thinking about how we might solve this problem. So if we just forget about the wall removal aspect of this problem, right? Let's just say that we have these zeros and ones, and we cannot travel on a one, and we want to figure out the length of the shortest path from the start to the finish. So for now, let's go ahead and pretend like this right here is a 0 instead of a 1, because otherwise it's not possible to solve this problem in this example. The way we would do that, we kind of know how to do that, right? You do a BFS where you start at the start node and you kind of go level by level outwards until you hit the finish point. And we would just write some logic that says, hey, if we ever hit a 1, just stop searching down that path because we're not even allowed to walk on that position. That's not too difficult given the knowledge that we already have. But I want to kind of go into a little bit more detail on what that solution would look like. Most importantly, the question of what information would we store in our queue? We've seen sometimes we just store the node itself, but sometimes we store more pieces of information. So generally, whenever you're working with a grid like this, to uniquely identify any one position, it's not sufficient to just say, oh, 0 is the value of that position, because 0 is all over the place. So the way we normally handle this is we store the row and we store the column. That's definitely going to need to happen here. For each element in our queue, we'll need the row and the column of it, so we can uniquely identify it. But you know what? Actually, before we do this, I want to go ahead and erase all of these numbers. We don't need them anymore, but I wanted you to get a sense for exactly why the output is 21 and how we're calculating that. Okay, so back to what I was saying. Each element in the queue is going to have the row and the column being tracked. And again, right now we're just pretending we can't remove any walls. Oh, so this down here should be a 0. Sorry about that. Okay, what else do we need to store about each element of our queue? Well, we also need the length of the path so far, right? Because if we're at this position, the value is 20. How do we know that when we go here, it's 21? Well, we know that it's 1 greater than the current position. So we need to know the length to reach the current position. So I'm just going to write this as length here, but it's like the length so far, or the length to reach the current position is what we're storing. And this is really it. If all we want to do is solve the case where we can't remove any walls, this is the information we need, right? We're just going to BFS storing the row, column, and the length so far. So you can imagine at the start node, that's going to be 0. We haven't, or at 1, sorry, because we're counting the start node. So we've traveled through 1 node so far. And we would keep incrementing it length plus 1 every time we go to the neighbors or children of a node. Whenever we hit 1s, we stop. We don't need to continue searching that path. We can just skip. And whenever we hit this position here, so row equals 0, column equals 0, we know that we've finished and we can return the length of that position. Now, the question becomes, how can we sort of generalize this or expand it so that it works in the scenario where we're allowed to remove a single wall? Really what this means, let's go ahead and remove, let's bring that back. Let's go ahead and remove this 0 right here and go back to the case where that is given as a 1. So the answer here would be 21 because we can go through this position. You can notice that, actually, sorry, let's make this a 0. If you started our start node and this was a 0, you could, oops, that was not good. You could go through the normal path, which is something like this, but there's a faster way, which is that you could go up through here and go through this, because there's only one wall, which is this one right here. All right, let me put an arrow, this one right here, and we can go ahead and remove that as our one wall. So there's a faster solution there that should have a length of 11. Let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, looks like 11 is the answer if we have a 0 in that position that I marked. So let us go ahead. We'll stick with this as a 1 for now. Now, we want to modify the information that we're tracking. So what is the implication of this requirement that we can remove one wall? To me, it really means two things. Number one, it means that previously we could say whenever we hit a 0, just stop searching that path. No need to search anymore. But that's no longer true. Now we should, in certain cases, continue searching even when we find a 1. That's the first thing that sticks out to me. But the second thing is there's also this scenario, which is like, let's say we go through, we start at the start node, we go through here, we come up here, and we're right here. And we're deciding, can I go up or not? We also need to understand that we have already removed one wall, so it is not valid for us to remove another wall. So it means 1, we can't just immediately skip once we find a 1. But 2, it means we also need to track how many walls have we already gotten rid of. And we need to know that really for every node, right? So at this point, we would want to say, okay, we've removed 0 walls. At this point, we say, oh, we removed a wall. At this point, we still need to know, hey, in the past, we've removed one wall, and all of these values should have 1 right here. So the way we can handle that is we can come up here to the information that we store for every single element in our queue, and we can add the number of walls removed. I'm just going to write this as walls for the sake of space right now, but we need to track the number of walls that have been removed so far. That way, we can say, if we are currently at a 1, then check the number of walls removed so far. If it's 0, you can continue searching, just bump that number, so it's 1 wall removed. But if we've already removed a wall, if it's 1 or greater, then just go ahead and stop searching. We're done. We can't continue down this route. So that allows us to address this question of what do we do when we're allowed to remove one wall? Now, there is another important thing, which is that whenever we do these types of BFS questions with undirected edges, and you can go from 1 to 0 like this or from 0 to 1, so we do have undirected edges here. You also have to worry about getting in infinite loops where you're handling nodes that you have already visited in the past. Normally, the way we do this, there are several ways to do it, but one way is you can have a Boolean matrix. That's what this matrix on the right-hand side is. The idea is that every position, you store a Boolean telling us if we've already visited that position. So for now, these are all going to be false. That's what F means. And the idea would be, as you move through them, you go ahead and flip them to true. So we start at the start node and we say, all right, let's go ahead and make that value true. We visited it. And you would write some logic that says if visited that position is true at our current position, just skip it. Don't do anything. The problem is that doesn't work for this question. And let me show you why. Okay, so now is when we're going to want to switch our value from a 1 to a 0 right here. Okay, so in the event that this is a 0, which it now is, the optimal path, just to highlight one more time, is starting here, going up through here, and then we want to use this as our wall we're going to remove. So we get a total of 11. Let's go ahead and mark that up here. Let's just say 11. Oops, let's go through that and say 11 is the shortest path, the length of the shortest path. Now, there is one path, which is, let's just say for now, our code, when we're at a particular node, let's say this node right here, this one, then it goes up and then down and then left and right. Let's say in that order, up, down, left, right is how we search. Well, when we reach this node right here, we're going to first go up. We're going to go to the 1 and we're going to say, well, have I already removed a wall? The answer is no. So it's totally fine for us to go up to the 1. So the path we're looking at is going to look like this, and then we can, the path's going to look like this, and then we continue onwards and we keep going. But then when we reach here, oh man, let's do that again. We go this way, go here, and we stop here. And we can't use this one as the wall we remove because that's not optimal. Because we've already removed a wall. But that's not optimal. We don't want to go all the way around like this when we know that there is a faster way. Oops, let's bring this back. So the question is, why can't we just go all the way left across and then come up here? Well, let me show you why. The issue is we would mark all these nodes as visited like this. True, 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 true. Everything that we go through would be marked as true. And I don't have to continue onwards. This gets the point across. Now you can imagine when all these are marked as true, we've already gone up from this node. And sure, we try going left, and maybe that works. Oops. That works, and then we mark it as visited. And then when we are on this node, I'll underline it right here, we try going up. The problem is when we go up, we reach this node, but it's already visited. So because of that, we are stopping. We are just skipping and moving on. So we're actually not even testing the scenario where, let me undo a bit to show you. We'll get rid of all of these visiteds now. We're not testing the scenario where we go this way instead of this way. So you can see there's an important pitfall here, which is that we cannot use a simple or standard way of tracking what's visited so far. We want to be able to say, if we find a more efficient path to the current position, let's overwrite the path that we already have. And when I say more efficient, really what I mean is a path that can get here by removing fewer walls than what's already there. So the way we're going to handle this is, instead of storing booleans in this matrix on the right, we're going to make this a matrix of integers or numbers. And what we're going to do is store the minimum number of walls required to reach a particular position. So for now, let's just start with infinity, or the maximum number in your language everywhere. I won't write out all of these, but you can imagine that all of these are filled out with infinity, or the maximum value in your language. So when we're at the start node, we'll realize, oh, okay, we got here without removing any walls, so we can switch that to 0. These all become 0. That's not too complicated. Then when we go up from this node, we get to this position and we say, okay, we removed one wall to get here. So the answer is 1 for this position. Then we also go to the left from this node down here, which is equivalent to this node, and we put a 0, right? And when we go from this position to the left, we're going to give it a value of 1, which is totally fine, and that allows us to explore upwards. But when we go from this 0 upwards, we can give it a 0. So we're going to say, oh, just go ahead and overwrite this. We don't even need the path that used 1 wall. We can do it better with 0 walls. That's the key to making sure that this works, is that this matrix on the right is tracking the minimum number of walls required to reach a particular position. So if we find a way to reach the same position with a fewer number of walls, we can go ahead and overwrite its value like you just saw right here. That's the key insight with this question. And as long as we do that, we will be able to get the shortest path, because we'll realize, oh, okay, there's a way to get to this position with 0 walls removed. So that's equivalent to this position with 0 walls removed. And that means we can continue searching. So what we'll do is we'll search up. So we go, we're starting here, we go up to here, we go up to here. And at this position, we can make our decision from before. We can ask ourselves, can we go up and remove a wall? Well, the answer is yes, because in this current line that we are using to search, we've only removed 0 walls so far. So we still can remove a wall. That's an important point that you have to make sure not to miss with this question. Otherwise, you can get some of the test cases incorrect. Okay, great. And one last thing I should mention is, every location in our input matrix corresponds to the matching location in our visited matrix, like this, like I've drawn here. We've seen that before. There's also the thing where people will try to modify the input matrix, like we've seen in number of islands or other questions like that. The problem here is that would be kind of difficult because we still need to know where our walls are and where the passable positions are. So I think it's much easier to have a separate visited matrix like this. Okay, now I want to go ahead and talk about the complexity of this solution, which is a little bit interesting. It's not as cookie cutter as it normally is, though it's not crazy difficult or anything. All right, so let's come over here and we'll write out our complexity. So the very first thing we want to do when we're dealing with complexity is we want to define our variables. So we're going to use v and e, which we've seen many times, number of vertices, and e is going to be the number of edges. But that's not all we're going to store. We're also going to have r, which is going to be the number of rows in our matrix, and c, which is going to be the number of columns in our matrix. None of this should be new, but it's kind of interesting how we use all of these together. Before we get to the complexity, I want to make one observation about the relationships between these variables. I'm going to say that e is always going to be less than or equal to 4v. So what I'm saying here is that the upper bound for e is just 4v. And the reason is because, let's start by thinking about what are the vertices in our graph. Well, that's just the number of positions that are here, right? Every 0 or 1 is a vertex in our graph. And the edges are invisible, but kind of go like this between all of the different vertices in our graph. So at max, each vertex will have 4 edges if it's something like this one right here. It could have fewer like this 0, but that doesn't really matter. What I'm saying is the upper bound, is that e is never going to be greater than 4v because every vertex can have at most 4 edges. Really what that means is O of e is equal to O of 4v, which is equal to O of v. Specifically in this case, that doesn't mean for all problems O of e equals O of v, but for our purposes, in this problem, O of e and O of v are the same thing. Okay, now let's write out the time and the space complexity here. Now, we know our time is going to be O of v plus e. This kind of thing we have seen before with our BFS. In our case, imagine if the entire matrix were zeros. Then every node would be put onto the queue, and we would iterate through every single vertex in the graph. That's where the v comes from. We'd also go through all of the edges because for each vertex, we're going through all of its edges, which means in total we go through all of the edges. But since O of e is equal to O of v, we can simplify this and just say the overall complexity is O of v. There's one other thing though, because we can express v in a different way. And let me ask you the question, rhetorically, how many vertices are in this graph? Well, we can actually determine that by looking at the number of rows and columns. So you can see that there are r rows here, and there are c columns, like assuming there are r rows and c columns, then we can say that there are r times c vertices, because we have one vertex at every position in this matrix. So we can write O of v another way as O of r times c. Both of these are completely valid descriptions of the time complexity. Similarly here, the space complexity is going to be O of, let's see, we want to think about what is the maximum number of nodes that will be on our queue at any one point in time. Actually, no, we don't even have to worry about the queue because we have that visited matrix that was on the right hand side. So remember, there's one position in our visited matrix for every position in our input matrix, or every node in our input matrix. So it's O of V for the space complexity, which is equal to O of R times C. For the same reason that I described above, because there are R times C nodes or there are V nodes. These are really the same thing. In an interview, I would probably just explain all of these complexities. I think it just shows that you understand the different facets of the complexity and you don't, like have a surface level understanding of like, oh, it looks like it's M times N, which is rows times columns. But you can really show that you understand how these relationships apply. So that is how you can express the time and space complexity of the solution for this question. That's all for the approach. So let's go ahead and switch over to the implementation. Now, let's see an example of how to solve this question in JavaScript. To get us started, I've imported the queue. We can see our example input and output right here. I chose to do the case, let's actually do this case where the answer is 11 because we can use this as our wall to remove. And here I've defined our test. Let's actually switch that to be 0, and then we're running our test at the end. Okay, so the very first thing I want to do is go ahead and create our visited matrix. So let's just say visit is going to be create array of size, and I'm going to make a function to do this in a second. And we'll grab these variables as well. But let's start by making this function just because it's a little bit unclean the way we do this in JavaScript. So we're going to say array is going to be new array. This is how many elements it's going to have on the outer level. But then we have to iterate through those. So go through array.length, i++, and we're going to say array at I is going to equal a new array of length, however many columns we should have. And then in the end, we can go ahead and return an array. All right, now as far as how do we grab the number of rows, we can say num rows is going to be map.length, num columns is going to be map at 0.length. And let's change this to be num rows. This is going to be num columns. There is the edge case that's often seen with these grids problems, which is what happens if there is 0 rows. Then line 34 would cause a problem when we try to do map at 0.length. So let's just say if num rows is equal to 0, let's go ahead and return 0. I don't think this is like even a reasonable input, so we don't have to worry too much about it. We can just go ahead and return 0. You could also throw an error if you want, or return null, or handle that however you'd like. Okay, now we want to start our BFS, but we also mentioned that we're going to store 4 pieces of information for every element in the queue. So I want to create a class for that. I'm just going to call it node. And what are the pieces of information that we're going to want to have? Well, we want to have the row value, which is going to be the row. We'll pass that in. We're going to have the column. We're going to have the length so far, which is going to be length so far. And we also need to store the number of walls removed. So we'll do that like num walls removed. And let us go ahead and make sure that all of these are parameters. This should not be this though. So here we'll say pass in the row, the column, the length so far, and the num walls removed. I'm going to write a quick method on here that's just going to be get properties. It's just going to return an array with all this information so that we can access it easily. And it'll take no arguments. So we'll do this dot column, this dot length so far, so far, and then this dot num walls removed. Okay. Now we have this node class that can store a piece of information inside of the queue. Now let's write the skeleton of our BFS. So we're going to create a queue, which is going to be a new queue. Let's create our initial node. So where do we start? Start in the bottom left portion of the array. So we want to create a new node. We're going to pass num rows minus 1 is the last row. Num columns minus 1 is the last column. We want the length of the path so far. So we should be including the start node itself. So it should be 1 at this point in time. And then we'll also pass 0 here, which is going to be the number of walls that we've already removed. It's guaranteed that our start node will not be a 1, so that's fine. Okay, now we want to add that onto our queue. So we'll say enqueue the initial node, and we'll start our BFS. So we'll say, so long as the queue has some elements in it, let's go ahead and remove that value from the queue. So we'll say node is going to be queue.dequeue. I'm going to grab the properties using this method here. So we're going to say, I'll use some destructuring here. So we're going to say grab the row, the column, the length so far, and the num walls removed is going to be node.getProperties, and we'll invoke it. To be clear with this destructuring, all I'm doing is just saying grab this, whatever is returned here, and store it in the row variable. I'm going to grab this property and store it in the column variable, and so on. So I'm just saying, match the names I've provided here with the corresponding locations in the return value from the getProperties method. Okay, so this covers how we get the nodes. We also want to process the node here, and then we want to add neighbors onto the queue right here. So the way we're going to do that is just go all 4 directions. So we'll say, let's enqueue, and what do we want to do? We want to go all 4 directions with 1 greater value. So let's do new node, because everything in the queue has to be a node. We're going to pass in, let's see, do we already have row? Okay, row and call are fine. I was worried that they were named the same thing above, but they're not. So we're going to do row column. We'll update that. Obviously, we don't want to do the same position, but the length so far is going to be whatever the current one was, because how did we get to like this node? But we have to add 1 more because we're traversing another node to get to whatever new node we're talking about. And here we're going to pass the num walls removed. We're going to pass new num walls removed, which we will create later on. We don't have to worry too much about that right now. But so let's say we want to go up for this. Oops, not 2. Here we'll go up, and then we'll paste this, and +1 will allow us to go down. And then we can do column -1 is going to go left, and then column +1 is going to go right. And the remaining pieces should stay the same, the number of walls removed and the length so far. That doesn't particularly matter. Okay, so we set up the skeleton of our BFS. Now is the interesting logic, which is what do we want to do for every single node? Well, the first thing is we need to return an answer somehow. And the way we do that is when we hit our ending position, which is the top left. So we'll say if the row is the 0 and the column is equal to 0, what we want to do is just return the length so far. That's pretty straightforward. We're just returning, what was the shortest path to get to this position. Now, we also need to figure out what is the new number of walls removed that we pass here. And that depends on the current value. If the current value is 0, we can just set it to be what it already was. But if the current value is a 1, then we have to increment it. So the way we can do it is we can say let new number of walls removed is going to equal num walls removed. And then we'll just simply say if we probably should grab our value in a variable. So we can say current value is going to be map at row at column. I'm going to put an asterisk here so that we don't forget something. But if the current value is equal to a 1, then let's go ahead and increment our count here. You could probably use the same variable. I think it's a little bit confusing that way, though, the way things get modified. So I'm personally going to do it this way. It doesn't matter too much how you do it. Okay, so we've covered how we terminate when we find our finished node. We've covered what happens when we are on a 1 so that we can track the fact that we have, just like hit a node. When I say hit a node, I mean hit a 1 node, and we've removed a wall. We want to handle that. And yes, okay. So we also want to handle the little asterisk I mentioned here, which is that, as you've probably noticed by now with grid problems, you always have to handle the case that your row or column get out of bounds. So we're going to say here, I'm going to actually write a separate function called shouldSkip that will give us this, that will return a Boolean that tells us whether or not we should skip. So I think these are the 3 properties it'll need, but we'll write that in a second. But we're saying if that value returns true, then what do we want to do? Then we just continue. We don't have to do anything, right? Yeah, that should be fine. I'm thinking we could put this first. It doesn't really matter that much because we know that row equals 0, column equals 0 will have a value of 0. That's guaranteed with the problem. So we're just saying if we should skip it, go ahead and skip it. Otherwise, do our logic. So check if we found our end, the escape pod. Then if not, then we want to see, should we increment our new num wall is removed, because maybe we had to remove a wall for this current position. And then we add new nodes to the queue. All right, so now we need to write this function, which is going to be a pretty important function for this question. So how do we want to handle this? So let's just go ahead and return true as our default, but we'll return false in special cases. So we want to do if the row is less than 0, we're going to need the map here so that we can know, how many rows and columns there are. So we can say if row is greater than or equal to map.length, we're going to return false. If column is less than 0 or column is greater than or equal to map at 0.length, we can return false as well. Now there is also I got these backwards. This is should skip. So in these two cases we should skip because it's an invalid position and the default should be returning false. Should be careful with how I name things. Okay. Now, the other case is if we have already removed one wall and the current position is a 1. So we can say current value is going to be map at row at column, and we'll say if num walls removed is equal to 1 and current value is equal to 1, then we return true. We should skip, right? Because that means that in order to process the current node, we would have to get to 2 walls removed, which is not allowed, so we can stop processing at that point in time. Okay, great. So we have now covered most of the core logic. The main thing that's missing here is we need to handle the visited matrix, which we discussed earlier. So we want to make sure that we don't get in these infinite loops, and we track which nodes we've already seen. So we created the visited matrix here, but we need to make sure that we're updating it. That should happen at the process node step because we want to do it for every single one of our nodes. Now we said that the value we store in the visited matrix is the minimum number of walls that need to be removed to get to the current position. So this part is accounting for the current position, but we don't care about that for the variable I'm talking about, the visited matrix. We care about how many walls need to be removed to get here, not including here. So before we do this update, so like right here, we want to say, let's update our visited matrix at row and at column. And it's going to be the minimum number of walls removed so far. So we're just going to, for now, just assume that this is the minimum. Obviously, it's not always the minimum. It's possible that this value is, let's say, 2 or maybe 1, but we've already found a way in the past to reach it with 0. In that case, we don't want to overwrite it right here. So what we'll do is we'll modify our should skip function so that we automatically skip whenever the visited value is already better than what the current value would be. So let's go ahead and check that here. So we want to say if visited at that position, so at row, at call, so we should pass the visited matrix as well. Let's come, where are we calling it? Right here. We're going to pass the visited matrix, and we'll say if visited at row and at column is smaller than or equal to, less than or equal to, the number of walls we've already removed, we can just return true. This is because we're saying we've already found an equally great or better path to the current node than what we're currently considering. So why would we, even search down this path? If we just now found a way to reach it with 1 wall removed, but we had already found a way to reach it with 0 walls removed, there's no reason to continue searching further because we've already found a better path, and that path is already somewhere in our queue. Okay, so that covers I believe, all of the logic. I'm sure I forgot something. There's a lot in here, but we can delete this. But the basic idea is we're doing a normal BFS. we're storing the length so far, which is needed for shortest path problems. We're also storing the number of walls that we've removed. That way we can make sure that, first of all, we're allowed to remove at least one wall, or at most one wall. But second of all, we also have to make sure that we don't remove 2 or 3 or 4 or whatever walls. So that's why we're storing that information. We also have this visited matrix that tells us the minimum number of walls to reach any particular position. This allows us to avoid any sort of infinite loops, so we still have the visited tracking, but it doesn't interfere with our ability to find the shortest path with one wall removed. So let's go ahead and test this out and see if everything works. So we should get 11 as the output. Okay. Looks like I might have had a new line or something, but that doesn't really matter. We got 11, which is the output that we expected. So let's go ahead and come to right here, and let's write the complexity of our solution. So we'll define V to be the number of vertices. We'll say E is the number of edges. We'll say R is the number of rows, and C is the number of columns. We also know from the approach that E is bounded by, the upper bound for E is is 4V. So we can say O of E is just equal to, oh man, I'm not typing well. Is equal to, O of V. Okay, great. So our time complexity is going to be a standard BFS, which is V plus E. Since E is the same thing as V in terms of big O notation, we can just bring this down to O of V, and that is also equal to O of R times C, because that's how many vertices or nodes are in the graph. In terms of the space complexity, it's going to be O of V for our visited matrix. It has one position for every node or vertex in the input grid. And that's going to, again, be equal to R times C for the same reason above, because that's how many vertices are in the input grid. Okay, that's all for this video, and I'll see you in the next one.